So welcome back to the discussion of patterns. Where we left off yesterday, I just described how the expression tree program was designed using an object-oriented design. Now what we're going to do is we're going to talk about the key patterns from the Gang of Four book that are used in the design and implementation of the expression tree processing app. As you can see here, there's about 23 patterns, depends how you count them, in the Gang of Four book. We're going to go through well over half, probably about 15 of them. Some, the ones that are checked with red, we're going to go through in a lot of detail. Other ones we're going to go through just sort of in passing. But this will give you a much deeper understanding of how the Gang of Four patterns are designed. Now, right now, I'm looking at the forest perspective as opposed to the tree perspective, no pun intended. We're going to go over a high-level view of the patterns and give you the big picture of how they're applied, and then we're going to start zooming into each one of them one at a time. So the Gang of Four book provides software design patterns, which are solutions to common problems that arise in a particular context when you build software. And there's 23 of these patterns. And as you can see, they're broken up into a couple of different categories. And we're going to talk about the patterns here. I will come back later after we go through the details of the patterns and talk more about the taxonomy. It's kind of like the periodic table of elements, how they're organized into class versus object relations and creational versus structural versus behavioral relations and so on. We'll come back and talk about those dimensions a little bit later, but right now I want to get into the patterns themselves. As you can see, we're going to focus on about a dozen patterns, and we're going to leverage them in the context of our case study, which is the case study app that we're doing. And as you can see, these patterns are there to help address various design problems. So the first pattern we're going to talk about, and again, keep in mind, this is a very high-level overview. We will dive into each pattern in much more detail, I assure you. The first pattern we're going to talk about is called composite. And its intent, what it's trying to do is it's trying to make it possible to treat both individual objects as well as recursively composed objects in a uniform way. And the reason for doing this is you want to be able to have kind of a common interface that works irrespective of whether you have one of something or a multiplicity of something. And this is used to help make your designs more extensible and less error-prone. So the design problem it's addressing is non-extensible and error-prone designs. And as you can see, when we talk about this in more detail, the way it works is it defines a common interface that everybody shares, both the objects that only have one instance as well, and those are called the leaf objects, as well as the objects that are composite objects that contain multiple recursively defined or recursively composed objects. And it allows us to treat them in a common way. And you'll see that this theme is actually becoming very popular in a lot of contexts. Historically, it was popular in things like file systems, where you wanted to be able to treat both files and folders containing files and other folders in a common way. More recently, when you take a look at things like reactive programming and reactive streams, you see that a real common theme is to be able to treat something that has one of something in an identical way as something that has multiple of something. And you treat them as a stream, which is kind of an abstraction that lets you gloss over whether you have one or many of something. So that's what composite's about. And you'll get a chance to apply a composite-like approach in assignment number 5, although we don't really take it as far as we're going to take it in this case study. The next pattern we're going to talk about is something called the bridge pattern. And the intent of this pattern is to separate an abstraction from its implementation so that the two can vary independently. And this is a really cool pattern. It's particularly relevant for C++, where you don't have garbage collection. You have to manage your memory directly and manually. So it helps to be able to use patterns like bridge to simplify manual collection of dynamically allocated memory. And I'll show you some cool examples of this. This pattern is also applicable in languages with garbage collection. For example, it's used in various places within Java, as we will also talk about here in a minute. And the purpose of this pattern is to minimize the impact of variability. And the way it does that is it defines an abstraction, which is an API, an application programming interface, that clients are going to access. And then it has a separate implementer hierarchy where you can vary the behavior quite in a quite clever and canonical way. And so by decoupling the abstraction or the interface from the implementations, you can plug in different implementations without breaking anything about the client interface. So that's a really nice, helpful way of dealing with certain things, especially in a language like C++ that doesn't have the benefit of automated garbage collection. The next pattern is called interpreter, and what it does is it takes a language, which is a computer language, not a human language, and it uses a representation for the grammar of the language, which basically says what's syntactically correct. And then it finds an interpreter that uses this representation to interpret sentences in the language. Now, if you've taken a compiler theory course or an automata course, this will make perfect sense. If you've never been exposed to sort of the theory of languages and formal languages in computer science, you're probably scratching your chin going, what the heck is he talking about? So we'll go through an example of this, but basically a way to think about this is when people have input, like you type an expression at a command line, then that forms a sentence in some language, such as the language of arithmetic expressions or algebraic expressions. And an interpreter is used to parse that expression to figure out whether it's valid and then figure out how to process it as well. So we use this, of course, in our expression tree program to take user input, and we do it in a way to make the user input as flexible as possible. So you can change the input formats without breaking a lot of the other parts of the code. And we'll see when we talk about this, we talk about things like terminal expressions and non-terminal expressions. And even if you don't have a lot of background in formal languages, I'll explain it in enough intuitive detail that it should make sense for our purposes here. Another pattern, which is related to interpreter, although it can also be used independently, is called builder. And what that does is it separates the construction of a complex object, like an expression tree or an expression, from the representation of the object. And we typically use builder when we're creating something that has multiple parts. And in our example, in our context, the expression tree that we create, which is a composite, is going to be created using a builder to build each of its different pieces, its different types of nodes. And in our case, we're applying builder to make the interpreter's output more flexible so we can change its output without changing other parts of the interpreter or other parts of the program. There's other uses of builder. It's very commonly used nowadays with so-called fluent interfaces, and I'll talk about fluent interfaces and how we use builder in fluent interface design. And this is, again, very, very popular these days in modern programming techniques. So basically, you can think of a builder as a factory with a mission, and the mission is to build some complex object out of its constituent parts. The next pattern is called the command pattern, and it's a very cool pattern. It encapsulates the request for a service as an object. So rather than having requests kind of scattered around and discombobulated in your program's global address space, instead we define things in terms of commands, and then we're able to treat them in uniform ways. So we can create a command, we can store the command in some kind of container, we can pass the commands around between functions, we can put them into run in a background thread. There's all kinds of things you can do with commands. And then when it's time to execute the command, every command is executed or run in a canonical common way with a method called execute. And this is a very popular pattern used quite a bit in user interface context to handle things like menu items. So if you're familiar with Microsoft Office or any of the Office suite tools like Word and PowerPoint and so on, the menu items that you can select are typically implemented as commands. And so when you click on open or click on save or click on save as or click on edit or whatever you do, that's actually executing a command under the hood. And we use this to be able to consolidate requests that users provide us in a canonical and common way. Another pattern, this is one of the most common and popular patterns in the entire Gang of Four book, is called factory method. And what it does is it decouples the interface for creating objects from the mechanism for creating objects. And so by decoupling object creation from object use, you can encapsulate or hide all the complex, messy aspects of creating objects that you have to do to make them from the use, which becomes very simple. So much the same way people like to joke that legislation is like sausages. It may be tasty when it's finished, but you really don't want to have to know how it's made, right? It's kind of messy and bloody, and a lot of compromises take place. Well, the same thing's true about object creation. When we create objects, we don't really want to have to know how they're created, because that's usually messy and ugly. But once we've made them, they're sleek and cool and easy to work with. And we do this, we use the factory method pattern all over the place in our program, as in most programs, to make it easier to create variabilities. So there's lots of things like commands that we create. There's composite trees that we create. There'll be other things we'll talk about in a moment called strategies or visitors that we create. And we always try to use factory methods to create them because it centralizes the interface for creating something, but leaves the choice of how it's created to some other mechanism that can be extensively modified and enhanced without breaking the clients that use it. Next pattern, another very common pattern. In fact, we've seen this pattern applied again and again in the context of STL. And this is the iterator pattern. So the iterator pattern allows you to be able to access every element in an aggregate without actually exposing its representation. And if you think about what we've been doing so far with the iterators in STL, in fact, the ones that you've been implementing, we're encapsulating the details of an array list or a vector or a deck or a map or a set or a tree or whatever. And we're hiding things in such a way where you don't actually know how it's represented, but you have a common way of being able to get access to each of its elements. And that common way is the iterator part. And then the implementation allows you to do whatever you need to do to have that common interface. So we use this pattern to be able to allow traversing of our expression trees in all kinds of flexible ways using a common API, using a common interface. And you'll see that there's different variants in the iterator pattern. There's the Gang of Four version, which I show you here, and we'll talk about shortly. There's a Java variant of this. There's the C++ variant of this. Lots of other variants exist as well. In fact, in some languages like Java, there's actually multiple ways to implement iterator. The next pattern that we'll be covering, and this is probably my favorite pattern in all of the Gang of Four book because I use it so frequently in my work, is the strategy pattern. And the intent of this pattern is to define a family of algorithms, encapsulate each one, and then make them interchangeable to let clients and algorithms vary independently. And we use this in order to be able to take lots of things that may change and have them pluggable in uniform ways. So it makes it easy to do plug and play like behaviors. And you'll see that the structure for the strategy pattern looks suspiciously like the structure for the bridge pattern. So they look similar from a structural point of view, but their actual behavior, their actual intent is different. And when we get to that part of the course, you'll learn how and why they differ. Probably the most notorious and infamous pattern in the Gang of Four book is the so-called visitor pattern. And the intent of this pattern is to centralize operations of an object structure so that the operations can vary independently, but they can be used in a pluggable way polymorphically. Now, one reason why this pattern is complicated is because nobody can make any sense out of its intent. And I have to confess, when I first heard about this pattern, I was mystified. When I explain it to you later, we'll see that it's actually not as complicated and scary as it seems at first glance, not as mysterious as it seems at first glance. But it is something that takes a little while to get your head around. And the reason it takes a while to get your head around is because there's two parallel structures that co-evolve. On the left-hand side, you have these things called visitors, which define the operations that are being performed. And on the right-hand side of the diagram, we have the object structure itself, which defines the various classes and subclasses and so on that are being applied, or having the operations applied to them. And that can be a little confusing. And there's also some other things like double dispatching and static and dynamic polymorphism that tend to throw people for a loop. But we're going to use this in order to be able to make the operations on our tree highly extensible. And I think you'll really enjoy learning this pattern. It's one of those patterns where once you understand it and you have a problem that requires it, it's wonderful and makes your life so much easier. And you'll actually get a chance to apply this pattern as well as many of the other patterns we've talked about in your assignment number 5. The next topic, this is also a notorious pattern in the Gang of 4 book. This pattern is not nearly as complicated to understand as the visitor pattern, and it certainly is not as complicated to understand its structure, which is, again, almost identical to strategy and bridge. However, the way it's applied makes it complicated, and this is called the state pattern. And the intent of this pattern is to allow an object to alter its behavior when its internal state changes. And what that means in practice is the object will appear to change its class. In other words, when you make an operation, when you make a method call on the object and it's in one state, the method will behave in a certain way. And when you make that very same method call on the same object, when it's in a different state, the method will behave differently. And so we sometimes call this the chameleon pattern, because it's as if the object is changing its state, it's changing its color. And a simple example of this, just to demystify it right off the bat, would be some kind of a file abstraction, a file object. And in a file object, the read and write operations should fail if the file has not been opened. So if you call read or write when the file object is in the uninitialized state, they will fail. After you've opened up the file object and connected it to a file, then the read and write operations should succeed. So that's a very simple example where the behavior of the operations will change based on the state of the object. And we use this particular pattern to ensure that user requests to our expression tree program that are called in so-called verbose mode will work properly. And if you don't follow the right protocol of the request, then it will fail properly as well. Next pattern, another very, very common pattern. It's the so-called template method pattern. And the template method pattern is designed to provide a skeleton of an algorithm in a method, and then it defers some steps to subclasses. And this pattern is used all over the place in frameworks, where you typically have some kind of abstract class or a base class with methods that are implemented in terms of methods that can be customized by subclasses. And we call these methods that have a behavior that is based on subclass behavior the template method. And we call the methods that can change the behavior of the template method either primitive operations, which is kind of what the Gang of 4 called it, or hook methods, which is the more modern way of referring to things. So you'll see that there's a concept of a hook method we'll talk about in the context of frameworks, and template method is a great example of hook methods. So basically what you can do is you can define certain steps in a template method, which is a fixed method. In other words, you designate those steps in the implementation of the template method. But then the behavior of those steps can be changed by subclassing or deriving from a base class or a superclass. There's also another pattern called the Singleton pattern. This is a notorious pattern, or maybe the most controversial pattern. It's a better way to put it. So the intent of the Singleton pattern is very simple. Ensure that you only have one instance of a class and provide a global point of access to that one instance. We're going to use this in order to avoid the limitations and the liabilities of using global variables in our solution. The problem here is that if you get carried away with Singleton, you can end up with code that's very brittle and hard to evolve. And so that's why it's so controversial. A lot of people think it's a bad idea. It is often a bad idea. The particular way we're going to use it, where we're going to use it in our assignment 5 because we only have a single universe that contains all of our planets, that's a reasonably good use of Singleton. So there are situations where it can be used. Just be careful that you don't get carried away and make everything a Singleton, because that carries on its own set of downsides and liabilities. Okay, so those are the patterns that we're going to be talking about. We will also, of course, talk about other Gang of 4 patterns along the way. We'll talk about observer, we'll talk about adapter, we'll talk about things like prototype and flyweight and so on. So by the time you're done with this part of the course, you should have at least a conversational knowledge of most of the Gang of Four patterns. I highly recommend you take a look at the Gang of Four book as you're going through the videos we record, and take a look at those patterns and learn them and read the descriptions in the book. They're pretty accessible. They always have an example. The examples are typically defined using C++. Sometimes there's a little small talk thrown in there, but by and large, it should be easy to follow along with how it's defined. Now, of course, we're using this in the context of our expression tree processing app, but in reality, you can use these patterns for all kinds of things. It's not just for expression trees. So be aware that I use this to make the examples more interesting and more lively, and you can follow along with non-trivial code. But in real life, these are very, very broadly applicable patterns.